In this lesson, we're going to talk about properties of functions, including domain and range. Let's recall what's a function. Well, function is a relation. So, what's the relation? The relation is any set of ordered pairs of numbers. So, any set of points in the system of coordinates represents a relation. So, if we have system of coordinates and a relation that consists of, for example, these 3 points, we can talk about domain of such relation, which is the set of all the first coordinates of those points. So, for example, if I project those points onto the x-axis, then the domain of this relation will consist of these 3 purple points. Similarly, if we project those points onto the y-axis, like this, then the range of our relation consists of these 3 green points. So, range of a relation is a set of second coordinates of the points. Now, a function is a special kind of a relation. It has a property that for every input you have exactly one output. So we are assigning a unique value from the range for every input from the domain. And here we have a diagram of 2 relations. One of them is a function, the other is not. So relation f is also a function because for every input we have exactly one unique output that is attached to it. For example, 2 is attached to 1, 4 is attached to -2, -1 is attached to 3. There is only one arrow coming out of any point from the domain. While relation h does not represent a function, is just a relation but not a function, because for a number -2 we have 2 values that are assigned to it. Like 0 is assigned to -2, 1 is assigned to -2, so we don't have the uniqueness of assignment. Therefore, the relation h is not a function. If we have a graph of certain relation, for example, like this or like that, then we have a very easy test to detect if something is a function or not. If for any choice of a vertical line, such vertical line passes the graph only in one place, then such a curve is a function. However, in the second case, we see that we can find a vertical line that passes through the graph 3 times, more than once. That makes it not a function. So again, to check if something is a function or not, we apply vertical line test, which says that a graph represents a function if and only if no vertical line intersects the graph at more than one point. Okay, let's try some examples. Decide whether each relation defines a function and give its domain and range. Well, here we have a relation expressed by listing a few ordered pairs of numbers. So remember that a domain of such relation is equal to the set of first coordinates. So what are the first coordinates? -3, 1, 2, and 3. However, the range is the set of second coordinates. So it is 1, -3, 0, and we already took the one before. So just 3 elements. Remember that when we list elements in a set notation, just a few elements, it doesn't matter which order we are listing them in. So we have listed domain, range, but is it a function or not? Well, to be a function, for every input I have to have exactly one output attached. Since I don't have 2 pairs with the same input, then yes, it is a function because for every input there is exactly one output attached. Yes, a function. In the second example, it's even easier to detect that this is a function. If you think about vertical line test, any vertical line, if you draw it here or there, or there, or anywhere, it will cross the graph only once. That means, yes, we have a function. Okay, what's the domain? Domain equals, well, we need to project the graph onto the x-axis, and which numbers will be covered? Well, looks like everything on the number line will be covered. So the domain is all real numbers, not a problem here. Range. To find out the range, let's project the graph onto the y-axis and see what will be covered. Well, everything until this point. So what's this point? That looks like it's 4. Therefore, the range is from -infinity up to 4. With 4, because 4 is also taken as a vertex. In the next example, we have a relation graphed as a set of ordered pairs of numbers in a system of coordinates. Let's see if this could be possibly a function or not. Well, it doesn't look like, because this particular vertical line will cross the graph twice. So it makes it not a function. Let's find out the domain and range. Domain. Domain is projection of all those points onto the x-axis. So if I project them, I have this point, I have that one, that one, that one, and this one. So let's list them. It is 0, 2, this is 2, 3, 4, and 5. What about range? Let's project our points onto the y-axis. So we have -2 here, -1, 0, 1, and 2. -2, -1, 0, 1, and 2. In the following example, we have a relation given by an equation, so we don't have a graph. However, we can still analyze what's going on with the y value when you have particular x. So if I choose particular x, can I actually assign to it a unique value y? Well, it looks like yes, because you have specific number, you can always subtract 1, you can always take square root as long as the x value was in the domain. Therefore, this is a function. There is a unique value y assigned for every x. Yes, a function. To find out domain, we should protect the radicand not to become negative. So on the side we can calculate when x minus 1 is bigger equal 0, well, when x is bigger equal 1. Therefore the domain is everything from 1 up to infinity. As a matter of range, we just need to analyze this expression. If I take a root of something, this root will always be positive. The least that I can obtain is 0. You can't have a value of a root negative. So the range will be from 0 to infinity. In the following example, we have a relation given by equation again. But this time, if I choose something for x, for example, if x is 0, then we end up with y squared equals 4. Well, if y squared equals 4, then we actually have two possible solutions. Our y could be plus or minus 2. So for the same x, 0, I can attach 2 or minus 2. That makes it not a function, since we don't have a unique value attached to the same input. Now analyze the domain of this relation and the range. Recall from the last lesson that this type of equation represents really a circle with center 0, 0 and radius 2. So it looks somehow like this, where the radius is 2 here and there. Well, when we see this circle, it's very easy to detect that the domain is from -2 to 2 and range also from -2 to 2. So we can give the answer, -2 to 2. In both domain and range, the same. The following example, we have a graph. As usual, with a graph, it's a lot easier to detect it's a function or not. This is not a function because we can get a vertical line like this, and we see that it crosses the graph twice, makes it not a function. What's the domain? Well, we need to project all the points onto the x-axis. This point is not taken, however, that one covers the last point, which is equal to 4. And since the vertex is at -2, therefore the domain is from -2 inclusive, we have this point included, till 4 square bracket as well, because this point will be covered by the point for -4. What about range? To see the range, we project all the points onto the y-axis. So it looks like this point will be projected and all the other points here, here, until we get number 4. But number 4 is actually not covered. It will be a hollow circle. So the range is this set from -4 inclusive till 4 without 4. And the last two examples, again, we have given relation in a form of equation. Similarly as in example E, if I choose a specific x, for example, -1, what kind of y will be attached to it? If x is -1, then y squared by itself will have to be 1. But that means that y could be either 1 or -1. Since there's two possible values attached to -1, therefore this is not a function. Let's investigate domain and range. Domain. What kind of axis can I have here? Since y squared is always positive and this negative in front tells us to take the opposite, then x will always have to be negative or possibly 0. So all negative x's and 0 from -infinity until 0 inclusive. And range. Analyze what kind of y's can I have? Basically anything. There's no restriction on the value of y, so range is all real numbers here. And we can recognize the graph of this equation to be a sideways parabola. Since y is squared and x is to the power 1, this looks very similarly to a regular parabola with equation, for example, y equals -x squared, except that the x and y have interchanged roles. That means we change the x and y axis. If we do that, then the graph of such a parabola, if this is your x and this is y, will be sideways going down like that. So yes, you can see that this is not a function. Domain is all real negative numbers plus 0, and range all real numbers. And finally, the last example. This is interesting example. We don't have equation, we have inequality. So is that a function or not? Well, definitely not, because for any x I can have tons of y values that will satisfy this inequality. Usually when you work with inequality, this will never be a function. Because inequalities usually produce infinitely many possible solutions. Usually inequalities gives us just a relation, not a function. But we can still talk about domain and range. So what's the domain here? Well, basically I can take anything for x. If I already have established x, then the y can be chosen accordingly. It's enough that the sum is smaller than 3. So the range, Well, the range could be also all real numbers. And to see that, it's a good idea to sketch the graph. We really deal with the linear inequality y smaller than negative x plus 3. So if this point is 3, and the slope is -1 of the related line y equals negative x plus 3, then the graph of such borderline will look somehow like this. And then y is smaller than it. That means every point that is below this line will satisfy such inequality. Now you can easily see that when you project the shaded region onto the x-axis, everything will be covered. And also when you project this region onto y-axis, all real numbers will be covered as well. Let's recall function notation. Instead of y value that is assigned to particular x, we would like to use the notation f of x. So you read this f of x, it's not f times x. Let's analyze what those signs really mean and why there is advantage of using f of x rather than just y. Well, f of x carries on a little bit more information. It tells me really what kind of y is assigned to the particular x. If I write just y, I don't know which x is this y assigned to, but if I write f of x, that gives me more information. What is the input and what is the output? The input is x, that's the independent variable. The output is f of x. F is the name of a function and f of x is the value of the function, the same as y. Usually f of x is defined by certain expression, so that's, for example, defining expression of some linear function. So looking at this particular example, if I want to evaluate f of 1, I am assuming that my x is equal to 1, so instead of x, you have 1 in the formula 9x minus 5, and then 9 minus 5 is really 4, so f of 1 is equal to 4. What does this mean? That means that the value 4 is assigned to the input 1 by the function called f, or we can say that the point 1, 4 really belongs to the graph of the function, or in other words, the ordered pair of numbers 1, 4 satisfies the equation of the function. Okay, now we have given an example of a quadratic function. We need to evaluate f of something, and this something is called a plus 1. So what we do, we write the function replacing x by brackets, because those are the unknown. Something is going to come to fill up those brackets. What's in the bracket is exactly this what you see in the bracket of f. So if we calculate f of a plus 1, your a plus 1 is your new x. So a plus 1 fills up the places where the x was before. And then we simplify. So perform perfect square formula. So it's a squared plus 2a plus 1 minus 2a and minus 2 equals a squared, 2a and minus 2a is gone, and 1 minus 2 is -1. This will be the output for the input a plus 1. Or, in other words, this will be the value of the function f at the point a plus 1. Similarly, in the second example, again, I will advise you to write the function by using a bracket instead of x. Everywhere when you see the x, put a bracket, and then fill up this bracket by the input -2c. So -2c over here and over there. The rest is to simplify. We're squaring the -2, so it's 4c squared. Two negatives make it positive, so it's 4c. That's the final answer. In the last example, we have a difference of values of function f at different points. So let's focus on the first one, just on this f. We take the input, square it, and subtract double the input. That's what the formula for the function says. The input is called 2 plus h. So let's plug it in 2 plus h here and there. And we're going to simplify in the next line. Next, we have a minus, so let's copy it. Since we expect that will be something larger after this minus, not just one term, because our function consists of two terms, so we need to put a bracket before we start writing what f of 2 is. F of 2 means that we replace x by 2. So we are going to have 2 squared minus 2 times 2. But the bracket is essential here. And finally, we just need to simplify everything. So perform perfect square, 4 plus 4h plus h squared minus 4 minus 2h minus, and this is actually 4 minus 4. We're lucky this is actually 0. So overall, we have, starting with h squared, will be h squared. 4h minus 2h is plus 2h. And 4 minus 4 disappeared, so that would be the final answer. Okay, we've been talking many times about graphs of a function, but what is a graph of a function? Formally, it's basically a set of ordered pair of numbers. X as an input and f of x, which replaces our regular y, is the output. So ordered pairs of numbers such that x comes from the domain of the function. D with subindex f represents domain of the function f. A piecewise function is a function defined by different expressions in different parts of the domain, some pieces. So we're cutting domain into sections, and in each section we can actually draw or define different types of functions. Here's the example. Our function f of x is defined in 3 parts of the domain. It is defined as absolute value function if the x's are smaller or equal -2, parabola if the x is between -2 and 3, and a linear piece of function when x is bigger equal 3. This wavy bracket here is used to indicate that we're talking about the entire function composed out of these 3 pieces. So the f is neither absolute value nor parabola nor linear. However, it has parts of those functions in it. So according to this notation, what f of -3 is? Well, I need to detect which part of the domain is -3 in. -3 looks like it's smaller than -2, so -3 sits here. Therefore, we're obligated to follow this formula. Therefore, f of -3 is the same as absolute value of -3 minus 2. And we evaluate this, becomes just 5. Now, f of -2, where the -2 is? Again, in the same part of domain. So it's here, because we have equation. It's not there because there's no equation, so we still follow the first branch of the function. Okay, so to evaluate f of -2, we follow the formula absolute value of -2 minus 2 equals, and that becomes 4. The next question is to evaluate f at -1. Well, where's -1? It looks like it's between -2 and 3, so -1 takes this branch of the function. So we're taking bracket -1 squared minus 4. We follow the parabola pattern. So this is 1 minus 4, it's -3 altogether. And finally 5. Well, 5 is larger than 3, so we need to follow that branch. Therefore, we should write 2 times 5 plus 1, which is 11. So now, since we already know how to evaluate piecewise functions at different points, we can use those points and use the knowledge of the nature of those functions in each part of the domain to graph the overall function f. Well, let's start with the linear part, with this section. I'm going to use green to graph that part. This formula applies only when x's are bigger equal 3. So mark the 3 here. Only in this part of the domain I'm going to graph linear function 2x plus 1. So normally I would start with 1 and go by the slope 2. So 1 across 2 up, 1 across 2 up, 1 across 2 up. my graph will look like this, but I start graphing it only from the point, which one is it? 2, 4, 6, 7. From the point 7 up with the same slope. So the graph will follow somehow like this. Now the middle section, which is parabola, I'm going to graph in blue. And this formula of parabola applies only from -2 to 3. So from -2 to 3, however, without the endpoints. So basically in this section of the domain only. How do we graph x squared minus 4? Regular x squared is a parabola like this. Minus 4 means that the vertex starts from -4 over here. And then go 1 across 1 up, 1 across 1 up, 2 across 4 up. Okay, so we know we need to end on this point, but we don't fill it up yet, because the endpoint should not be taken. Maybe to be more exact, it's a good idea to check what would be the value of this parabola at 3. If I plug it in 3, square it, that's 9 minus 4. The value would be 5, which is here. So I can go with my graph up to the number 5. However, I need to put a hollow circle at this point because it's not taken. This point actually belongs to the green section. So we have a jump at this point. And finally, in purple, I'm going to graph the first part, which applies to numbers lower than -2, and the function is absolute value function. This absolute value function normally would have a vertex at 2, so the shape of absolute value will look somehow like this, but we're graphing it just starting from the point -2. Since the value of this function at -2, we already calculated, it's 4, so we start our graph from the point 4, and then you can either check some other value or predict how the shape normally would look like. It would look like this. So the slope of the line will be -1, and it just follows that road. You can double check at the point -3, for example, if you plug it in, the value would be 5. So yes, that confirms. Overall, we've got a diagram of a piecewise function f with a linear part in the first section, quadratic part in the second section, and again linear part in the last section. So the purple one belongs to this part of the domain, -infinity up to -2, including the -2. A special type of a piecewise function is step function. That's really a piecewise function such that each piece is a constant horizontal segment. So here we see an example of a step function, and we have a formula in different parts of the domain. We have different values, but those are constant values, not any expressions that involve x, but just stable numbers. An important and very special step function is something that's called greatest integer function, or sometimes it is called floor function. The notation of it is by this double bracket, or floor function by single bracket, but with only those hanging out at the bottom and not in the top. Sometimes, especially on the calculator, this function can be denoted as int of x. Greatest integer that does not exceed x. That's the definition of the function. So if we imagine a number line and 0, 1, 2, let's say -1 here, pick a number x, for example, somewhere here, the greatest integer of this x is actually the integer that is closest from the left to this particular point x. So the greatest integer of this point will be 0. The greatest integer of 0 will be still 0. The greatest integer of -0.9 would be something that is an integer the closest from the left, so it will be -1, and so on and so forth. The formal definition, greatest integer of x, is such an n that x sits in the interval from n to n plus 1. This x particularly sits in the interval from 0 to 1. Therefore, the left-hand side of this interval, that will be the value of the greatest integer of x. So let's graph this greatest integer, maybe by developing some values, table of values, if this is x and this is greatest integer of x. Let's investigate the segment from 0 to 1 first. If x is 0, then the greatest integer is still 0. Basically, if x is any integer, the greatest integer function doesn't change it. It's still the same integer. So we have to mark 0 and a 1 and a 2. Greatest integer of 2 is 2 and a 3. Those points for sure, because they are already integers, so that's not a problem. If I have some larger number, let's say 0.4, 0.1, 0.5, anything between 0 and 1, even 0.99, the greatest integer of it is still 0. So I can go with my points all the way until 1, but not at 1, because exactly at 1 the greatest integer becomes 1. Now if I have 1.1, the greatest integer that does not exceed this number is 1. So for any number a little bit higher than 1, the value of our function is still 1. And that happens until we reach 2. For example, 1.99, the greatest integer of it is still 1. However, at 2, the greatest integer is 2. So we jump from 2 to the 2. And then a little bit more than 2, we still keep the value 2. However, at 3, we skip to the 3. And so on and so on. As you see, those will be like steps. That's why it's called step function. Now let's choose a couple negative numbers. For example, negative 0.9. Well, negative 0.9 is somewhere there. The greatest integer that does not exceed this number is negative 1. So the value for it will be here. And so on and so forth until we reach 0. No point at 0, because at 0 the value is 0 already. Similarly, before, that will be the step, and follow that pattern. This is greatest integer function. Okay, so what if I will ask you about domain of this function? Well, any x can be taken with no problem, and we can find out the greatest integer of it. So the domain is all real numbers. A little bit more interesting is the range of it. Observe that to get the range, we project the graph onto the y-axis. So we'll get this point and that point and this point and this one and 0 and 1 and 2. And as you see, those will be all integers. So it will be z, capital Z.